Now let us consider some dynamical aspects of electrons in band theory. It is useful to introduce the concept of velocity, quasi-momentum and effective mass for an electron in a band within a semi-classical picture. If we consider free electrons, then the wave function is given as W, which is a function of k and x, equals 1 over square root of L e power I k x in one dimension, with energy E k equals h cross squared k squared over twice m. The plane waves are eigenfunctions of the momentum operator. The momentum operator P is represented as minus I h cross d dx, and these wave functions are eigenfunctions of this operator with eigenvalues h cross k that you can readily see. If we now consider an electron in a periodic potential, then its wave function is going to be a Bloch function. So let's write down a Bloch function. Psi kx equals e power I kx multiplied with the periodic part u kx. But this in general is not an eigenfunction of the momentum operator. If we operate the momentum operator on this, we get minus I h cross d dx of e power I k x times u k x. Now this quantity, by performing the differentiation, we get h cross k psi kx plus e power I kx minus I times h cross d dx u kx. Now depending on the nature of this quantity u kx, if its derivative goes to 0, this would be an eigenfunction of the momentum operator, otherwise it is not. So in general, Bloch functions are not eigenfunctions of the momentum. But we have already discussed that the Bloch function can be represented as a linear combination of the plane waves. So the only possible outcome of measuring the momentum on a Bloch function would be one of the eigenvalues of the elements in the linear combination. That means we can have h cross k, a plane wave with this momentum. We can have h cross k plus minus twice pi over a. We can have h cross k plus minus 4 times pi over a, and so on. Any of these could be the outcome of the measurement of momentum, because we can represent a Bloch function as a linear combination of plane waves with this momentum. Therefore, we can call h cross k as the quasi-momentum, or the crystal momentum, because this is one of the possible outcomes of the measurement of P, measurement of momentum. So all these are also the possible crystal momentums, crystal momenta. Now let's consider the expectation value of the momentum operator in a Bloch state. The expectation value of the momentum operator would be given as psi kx p psi kx. Now if we divide the momentum operator by m, we are getting the velocity, and this kind of representation gives us the average velocity, which we can calculate to find out 1 over h cross dE k dk. Therefore, the velocity vanishes at the band extrema. If we go back to the band picture here, then the extremum is here, 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 and so on, and at the here, and so on. And looking at this picture, you can clearly see that dE dk, that is the first order derivative of energy with respect to k, is 0. That is, these are points of maxima or minima. And in that situation, the velocity of an electron would be 0 at these points. That's what we find from this expression of the average velocity.